Hello, everybody, and welcome to this AJS. The seminar is recorded, so it will be uploaded on the Science Chapter YouTube channel. And okay, we can start. Today with us, we have Nicola Demo from the MATLAB group, and we will talk about machine learning and retrieval modeling for real-time solution of nonlinear problems. So, Nicola.
Thank you, Priya, for the introduction. Thank you for being here. For those of you that doesn't know me, my name is Nicola Demo. I'm a researcher here at the SISSA MATLAB group since the last 6 years, more or less, even 7, close to 7. And yeah, today the idea is to try to share with you 3 different works that we did here, basically to try to tackle nonlinear problem. So just a bit more of the context where we are. We typically we are in a group that its main focus is about reducer modeling. So typically we use such kind of model in order to reduce the computational cost of simulation, let's say. So you have to solve a PDE that, in this case, for all this talk, is a parametric one. And the idea is, instead of redo a lot of times with the same computation with different parameters, we can try to save some computational cost using, for example, in this case, the POD model. POD means orthogonal decomposition, is one of the most popular techniques in the last year in order to achieve this kind of reduction. And I don't want to basically stress too much about the method. It's basically a sort of matrix decomposition, but the very take-home message is the fact that given as input a set of solution is able to give you the global basis that optimal represent your initial snapshots or your solution in a linear way. These global bases can be used in 2 different perspectives, let's say. So the first one is, of course, you can just think about the finite element somehow framework. You have that you have a lot of local bases that is basically are the one you use to assemble your discrete operator. In the POD hierarchy, instead, you avoid to use a lot of local basis function, and you have few of them that are global. So you save a lot of degree of freedom, because instead of having like 1 million per 1 million matrix linear system to solve, you have, I don't know, 10 by 10 system to be solved. On the other way, we have instead the aspect that we call non-intrusive, in the sense that here, of course, you have to reassemble your operator, but with a very smaller matrix. Here, we don't even know your actual operator, in the sense that you take some snapshot, so the snapshot that you collected also to build the POD basis are basically compressed or projected to the POD space. And so you have at the end that for any snapshot you collect at the beginning, you have a reduced representation of all these information. So you can just exploit the low dimension in order to basically create an interpolation and having, let's say, the parametric manifold approximated with the technique that you prefer. PODs work quite well. If you have a linear problem, probably is one of the best solutions still to take, but of course, it suffers in some other condition. And especially, let's say, for the nonlinear model. So just think, for example, on Navier-Stokes equations, where you have the vector term that basically make the problem not linear anymore. And for all these parts, basically, machine learning can help a lot. So first of all, of course, you are here, you're scientists, so I think that I don't have to explain so much the, let's say, the popularity of the machine learning in basically all the contexts. And instead, I just want to let you think about the similarity that we have between machine learning, so the standard machine learning, and the reducer order modeling techniques. Because in both the cases, you have the offline-online split for the computational perspective, in the sense that you need a lot of time to prepare your model. Is actually what in the POD base is the collection of the solution. They require a lot of time because you have to solve your parametric partial differential equation for several times. And this is, of course, you have to do with the standard way, so finite element, finite volume, whatever. But at the end, if your simulation is quite complex, you have to spend a lot of time just to prepare all that solution. Of course, you can have the reduction at the end, but I mean, you have also to consider that to have the reducer of the model, you have to prepare, I don't know, hundreds of solutions. It's not for free. In the same way, in the machine learning, we have the typically, especially talking with neural networks, you have to spend at the beginning a lot of time just training the model. So in my opinion, these two aspects are very, very similar and helps a lot to basically integrate everything into a unique frame. Also, yeah, basically you have also the same goal for machine learning and reducer order model. So at the end, you want to have a model that is very, very easy to infer. So you need like your solution in a few seconds, maybe a few minutes if it's very complex, but typically you want real-time frame. So also the state ROM and machine learning can work in the same way. And another, yeah, the last point is, in some sense, since yeah, actually a lot of people claim that they do machine learning, but at the end are just some more exotic term for all the stuff, let's say. In one sense, also reducer order modeling can be think like machine learning algorithm itself, in the sense that you are learning from your data, because the global basis that you compute are actually depending on your problem and the data you are collecting. So it's very, very close. Because of that, of course, we have a lot of integration between reducer order modeling and machine learning. So I just put some keywords here. There are probably a lot. I miss many important arguments, but at the end, I just want that you know that there can be autoencoder to basically replace the POD in a nonlinear way. You can have the POD with neural networks. So remember the POD interpolation that I told you in the previous slide. Of course, in this case, the neural network is used to basically construct the mapping between the parameter and the model coefficient. So the reduced representation of your snapshot. You can have also graph neural network, which is one of the most popular topics in the last year, in my opinion. The idea is you have a network that is not anymore a feed forward, but is basically has a graph structure or can act over a graph structure. So the input is not anymore just a tensor, but is a graph itself. And yeah, also all the latest part regarding the physics information part. So the way that, I mean, you want to try to learn actually your operator in your equation, just using the physical knowledge that you have about the equation that govern your problem. For this talk, I skip, of course, all the topics that I already mentioned, and I want to focus on these three main pillars that we're going to see in detail in the next minutes. So we have three different levels of complexity basically regarding the integration with machine learning and POD. So in one way, we have this kind of pre-processing that is operated by a neural network in order to transform your snapshot before applying POD. In the middle pillar, we have instead that we actually try to replace the POD with a convolutional filter that we basically implement here at SISSA. And in the last instead, we have another example where machine learning is used at the end, like post-processing step where typically, where you wanted to exploit a neural network to learn the error that the POD is putting in the approximation. Okay, I hope that in a few minutes everything will be more clear. So we start then with the first method that, of course, is not done by myself, but we have also two guys, not really young guys, but anyway, Michele and Gianluigi, that probably all of you already know. Also Giovanni, that is not anymore in SISSA, but I think you know him as well. And Davide Papapico, that was a former master student here at SISSA. So this is one of the most criticality of the POD model. Typically, you have one advective field. In this case, I tried to simplify it with just a Gaussian wave that is moving in time along your spatial dimensions. And you can see that even by looking at it with human eye, you're able to see that actually the structure that is moving is quite simple. So one maybe can think that the POD is able to detect that you have just one dimension, since it's just the same way that it is moving. But if you try to collect all the snapshot, you put in a matrix form and you perform the POD, you can find that the singular value. So typically, you can think like an extension of eigenvalues gives you some information about the real dimension that you need to put for your POD space in order to get a nice result. Basically, sucks for that specific problem. Even if the structure is very, very simple, you have the singular value that they don't show any low dimension explicitly. We know that, of course, we know that from here, but one solution can be simply shift your snapshot before doing the POD, because if you're able basically to align all these waves and you put in your matrix and you perform the POD, then your singulars value tell to you that you have just one dimension. That is, of course, what we expect, just looking at the structure. So then this work, the neural network shift, the POD, basically wants to learn such a shifting just using a neural network. So I don't want to go to the snapshot and say how the quantity that any snapshot should be shifted, but I want that all this quantity are computed just by a neural network. So the idea is we have two different networks. I'm going to start from the first one because it's the most intuitive one, and then I try to give you the information about why you really need a second network in this case. So the ShiftNet is actually the network that takes as input your snapshot, and it translates forward and backward depending to minimize a certain loss function. So everything is unsupervised in the sense that you have not to be supervised because the training is supervised, but you don't have to specify the quantity of the shift for any snapshots. Additionally, this is a tricky part, I know, but try to follow me. You need an additional interpolation network. This is a network that just performs an interpolation or regression. Call it as you prefer. With neural network, actually it's a regression, but you can think just as an interpolation. What's the problem? So you are in some spaces here. So all the snapshots you have collected lives in some Hilbert space, typically. So your snapshots are not continuous, are just some scatter points that you collected into a discretized space. That means that if you need to compare your reference configuration, that is basically the configuration that should be closer to the snapshot that is shifting, you need somehow to have a continuous representation of this reference configuration. In a few moments, I have some images that hope that help you in understanding these steps. But at the end, this is needed just to have a continuous representation of your reference configuration. This is the all you need. And here I try to summarize a bit what is the main step of this algorithm. So at the beginning, you need to select this configuration. You have, I don't know, hundreds of snapshots. You select the one that is basically you have to consider like a good configuration, in the sense that all the other snapshots will try to convert to be similar to that specific reference configuration. That, of course, you train the interpolation net in order to learn the continuous representation of this reference configuration. So just think of the wave is a way to go from the scatter points to a continuous way, a continuous function. And once you are done with the internet, you can also train the shift net. So at the end, you have simply that you do like a preprocessing operations on your snapshot, and at the end, you can apply the POD in the standard way. So you take your algorithm, you take your method, you take your software, and everything is the same. Okay, so let's understand a bit more about this shifting. Here is an example that we did with, it was a 2D wave, so still a wave that is moving into this domain. So we have three colors here. Basically, the green one is, I mean, just to think a time-dependent problem where you have some structure that is moving for some advective field, so some transport field. So you have basically that this wave is moving in this strange behavior. We don't know that. We just collected the snapshot, but at the beginning we choose the reference configuration that is more or less in the middle of the domain. Just think about, you have to choose the reference configuration as the easiest way to somehow be closer to all the snapshots in a sense. So you start your training with the shift net. You have this blue wave that is the candidate, and so is actually the test snapshot here that after certain epochs is moving, is converging from the blue one. You see in the last image is basically overlapping the reference configuration. So this is has been done just with a network that takes your spatial coordinate and your temporal coordinate and gives you the new set of spatial coordinates. So this is basically the ending of the story. So you have your snapshot that is defined by a scatter of points. You have the spatial coordinates and the field itself, that after the shift becomes something like that. As you can see, the shifting is added to the spatial coordinate, and this is, of course, the result of the net. So, yeah, sure. Okay.
How do you define the reference coordinate, each reference point?
You have a database of snapshots. You have to choose among one of them. No, one of them is your reference configuration.
Okay. Means so it depends on us like this.
It depends about the problem. Yeah, I mean, this is easier to see. So you have a lot of snapshots. Maybe I can take the red one, like the reference one, and so all the other snapshots are moving towards the red one. But you have to choose one because at the end you want to reach this stage. So everything is more or less aligned, and you can then apply POD.
The loss is basically x to the minus x MSE of it, is it?
Sorry?
The loss function is x tilde minus x the MSE of it, is it?
The loss for which?
This case.
For the shift one?
Yeah.
No, it's much more complex. You know, I don't know if I would right there, but no.
We are happy for complexity.
No, the problem is again about the fact that, okay, here I'm representing everything like a continuous field, but at the end it's not continuous. You have some discrete field on some discrete space at the end. So here, what you can't see basically from this simple slide, I know, but a matter of time, I can't put all the details there. Inside the training of the shift net, you have also to ask for an interpolation network. Because I think it's easier also in 1D. I mean, you have all these points, but if the shift, I mean, if your discrete space is not regular, I mean, you are not sure that moving forward of a certain quantity you are evaluating the same, the two different snapshots at the same coordinates, so in the same space actually. So you need an interpolation in the middle to basically project the reference configuration onto the spatial coordinate of the shift snapshot, and then you can do basically the subtraction. Is just I have two difference in this case, so it means for error typically, but all over the snapshot. So this is the quantity that you are minimizing.
Okay, so that goes from the interpolation, and that interpolation value, whatever comes out of the network, you subtract it with the rep, and that becomes the loss.
Yes.
Okay, perfect.
Because at the end, if you try to see everything, it's going to convert into, let's say, the aligned section.
So you have two networks with one loss function.
Yes, but no, you have also two loss function, because the internet has, should be trained before. You see?
Okay.
To train the ShiftNet, the internet should be already accurate, because otherwise you put a lot of error there.
But when you train this together,
No, this is trained before,
yeah,
and then you can go there. But this is just, you have export, anyway, I have a slide for that, so maybe it's better to show this one. So, okay, this is simply the idea of internet. You have the green reference and configuration needs to be approximated with a continuous representation. So here I show the same picture of this one, so different epochs of the same training, but here the goal is the black lines that are the contour line of the prediction of the network should converge at the end to the reference domain, to the reference configuration. Okay, so here you have the green one is discrete, and you have only the points. Here you have the value that is you have the value in all the domain.
Understood.
So you can do any computation you want.
So if I may ask, what is the properties that you're preserving for internet? Is there something that you have preserving something?
No.
No.
It's just an interpolation. Neural networks work very well to interpolation.
Okay.
If you have enough data, you can reach like 10 to the minus 6, 10 to the minus 7 in the loss. That is.
But a different, another very separate thing I was thinking of.
No, it's very simple. The internet is probably the most simplest network you can think of.
Okay,
so don't worry. And here just some conclusion, because yes, it's quite late. So everything is data driven. Remember that, because I don't put any information about the equation, the knowledge I have of the model. We just take the snapshot as you done in a standard PUD framework, and you try to improve a bit their quality. Is of course well suited for advection problem. So if you have a structural problem that is linear, please don't go for this solution, because I don't think it's able to improve your results. But if you have CFD, yeah, probably is a nice try also. In this case, of course, as you can see here, the shift, so the quantity that you have to shift at any point depends on the x and on the time. That means that you are not, you're not really moving your snapshot forward and backward of a fixed quantity, but it's not uniform, it's not constant, the shift that you perform. Like, for example, in the original framework, so the shift POD was already explored in literature, but they perform just a rigid translation of the entire snapshot. Here, we can basically compress a bit the snapshot, so we can have much more complex effect that at the end just try to help into the quality of the POD space. Of course, if you have a very complex problem, like one way that is splitting in two, we are completely lost, because we need to, this method works fine well, but if the same structure is more or less preserved for all the parametric or the temporal manifold. And of course, you have two different networks in the pipeline. So this is, of course, two additional sources of errors. So just think of that. If you have a very, very good POD, like my POD model is able to reach precision of 10 to the minus 5, yeah, probably think that, it's not said that with two neural networks, you are able to improve that result because anyway, you are approximating all of these steps. But here, just the final plot where we tried this, I think, is a multi-phase problem we try to tackle with this procedure. And as you can see, the POD singular values that we are able to extract at the beginning without any preprocessing on the snapshot are quite bad. You can see that there is no a very evident decay, so it's not able to really see the intrinsic dimension. Whereas in the manually shifted, so the red one are the almost optimal one because we take a problem, a benchmark where we know everything about it, and we manually translate the snapshot looking at the velocity field. So this is basically the best we can do with this framework. And the orange brown, I don't know the color. The dots, the orange dots are in the middle. That means that at least our neural network is able to not get worse results than the standard one, and it also is not able, of course, to reach the perfect one, but it gave you, like, with the same number of dimension, I would say at least 2 or even 3 order of magnitude more in the accuracy. It is quite enough. Okay, let's move very quickly because I don't have so much time. So time to move into the continuous convolutional filter that has been recently published this week, actually. That has been done here at SISSA with Dario, Laura, Giovanni, and Gianluigi. And the idea is, as I told you in the introduction, convolutional network, convolutional filter are impacting a lot in different fields. So, especially for the computer vision, blah, 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 you have basically that all the methodology are now based more or less on convolutional neural networks. What's the problem? Dealing I mean, everything is fine if you deal with images because you have a structured grid of pixels, and so you can apply this filter. But what about if we need to tackle an unstructured grid? So you do the simulation with finite element, finite volume. Typically, you don't have structured grid, but you have, I don't know, adaptive refinement, whatever. So this structure is not really exploitable anymore. I mean, just maybe to give you, to spend some words, this is typically how a convolutional filter works. So you have a filter here that is trainable. So any of this number in this 3x3 matrix is our degree of freedom that you can learn during the optimization step. So you just take a part of your images, you do the convolution. So you multiply any element and you sum everything at the end, and you get the result. So somehow the result of the convolution is actually your output. What's the problem losing the structure of your data is that, yeah, I mean, you can't do any more of that. So we think like this is the filter. So this is exactly, not exactly, but very similar filter to that one. You have, in that case, a 3x3 matrix. Here is 4x5, 4x4 matrix that is moving and is basically doing convolution in order to minimize a certain loss. So all these degree of freedom are trained during the epochs. What about if we don't, we don't keep like 16 degree of freedoms independently, but we have some other surface that is defined by some degree of freedom that basically perform the same operation? We basically ended with this continuous convolutional filter. So I try to summarize, to sketch the scheme here, just to provide you the graphical idea. So you have here this thing, just like this is your input images or input mesh. It's not structured anymore. You have some triangulation over there, but at the end you can have these boxes that are moving around all your domain. So you can perform an operation that is very similar to this one, just having a kernel that is continuous, and this is defined by another neural network, of course. This is a multi-layer perceptron, so actually the simplest network you can think of. And the idea is the same as before. Before you go from the image, you extract the patch, and you perform element-wise multiplication, and you sum all the components. And we do here the same thing, actually. So we take these points, the color should be like the heat map. So I try also to put some color. It's not really understandable, but yeah, at least give you some color. So you extract the points for a specific stride. So for a specific position, you have that basically you can evaluate your kernel at the same points. So I take the points, evaluate the kernel on the same. I have some values on these points, and I can multiply element-wise as I did in the standard convolutional filter. So at the end, you have just one number that is in the middle, of course, of the stride of the position that is not anymore really a convolution, but is like, I don't know, an integral, a mean value, something like that. I mean, here you are. Don't forget that here you are in a fixed space, like 3 by 3. Here is not. So it's not anymore a convolution, but it's very, very similar. So what is the idea? We can basically apply this filter to try to reduce all our snapshots. You don't need anymore to interpolate your snapshot from an unstructured grid to a structured grid, but you can just have to put this filter instead of the standard convolutional one. Okay, and of course, we try to do that with an equation, a problem that is not that difficult, but is something that POD already show some limitation in. Especially because we are in a nonlinear problem, in this case it's an Aristotle, but with a very low Reynolds number, so actually you can obtain very good result even with POD. But and for this case, we just try to use an unstructured grid to feed an autoencoder with this kind of filter. Here, of course, is not just a continuous convolutional filter, but we have also some multi-layer perceptron in the middle. What's the important part? You can take, you have this filter, but the very important part is that you try to reduce the dimensionality in an unsupervised way. So at the end, you jump off with this intrinsic dimension that is basically able to represent at the end your snapshot. So the idea is you train an autoencoder, maybe someone is not that familiar, but yes, the input and the output that are the same thing. You just need a network that is compressing as much as possible the information you are passing through this network, because in this case, you have somehow a reduced coordinate that helps, basically represent your initial snapshots. And just to give you some numbers, also some tests, this is a problem that is parametric. So we have, of course, different solution for different inlet velocity. In this case, the parameter is the water velocity here on the left side. And as you can see, we tried, now in this case, there is not the comparison with the POD is after, but we try also with a standard multi-layer. So avoiding the continuous convolutional part, using just multi-layer perceptor to compress everything, we get a very, very good result. Also, we are extremely happy to see that we are good also to generalize. It is not really, especially with POD, most of the time you can see that people present the train error that is very, very far away from the test error you can have. So don't just look at the train error when you try to basically measure the accuracy of your model. Another problem, we take it with the same methodology and with a very, very similar reduction, because also in this case we have an autoencoder that is composed by convolutional layer, and basically we have just an additional network to map the time instant to the intrinsic, to the low dimensional coordinates. So if you try to put the POD on the top line, you can see that it's actually the POD with interpolation of POD with neural networks, in the sense that you are mapping the parameter to the latent, you reduce the reduced dimension thanks to a neural network, and here instead of having the POD, you have the autoencoder. It works better than the POD from this images. I don't know how many of you have tried to tackle this problem with the standard POD, but typically if you have a very step interface in your problem, POD quite sucks to represent everything. Instead, in this case, this is, of course, the original one. This is the one we predict thanks to this network. As you can see, we are very able to basically individuate all the important factors. Also, I want to point you that even the effect on the boundary, it is due to the fact that this actually a CFD simulation where you have some boundary effect on the right part is catch by our autoencoder.
I'm sorry, I'm lost.
Yes.
I understood that continuous convolution was something to matching unstructured data, scattered data to structured. And
No. I mean,
what is it? Can you explain one more time?
Yeah, continuous convolutional is not a way to pass through from unstructured data to structured data. It's a way to work with convolution directly on unstructured data. Right. So, what's the point that is not really clear to you?
Yeah, the examples you just showed, I didn't understand. Can you explain more about the loss space, for example? What was your purpose of the simulation?
Reduce the dimension. I will say, I mean, everything here has been done to have a model that is very fast to infer for new parameter. That's the aim of the scope. You want to train this model with, I don't know, 10 snapshots, but you want to have the solution for the infinite number of time instants you have in your problem. Is basically the goal of all the reduced order modeling application, in my opinion.
So you
this is just a model reduction.
Okay.
But with an autoencoder at the place of the standard POD. So exactly, I told you if you try to put the POD here,
yeah,
okay, avoiding the other part because you don't need in the POD, but it's actually POD with interpolation, POD with neural network.
Now I understand. So somehow the continuous one is in the middle of the encoder and the image just.
No, the continuous convolution basically are the encoder and decoder part. Yeah.
So it is a central convolution. What's the difference? You mean in a sense, different is that it can get a scattered data, yeah?
It can
get a scattered data.
Yeah, exactly. This is a very important difference. I'm not claiming this is in absolute sense that better than the previous convolutional one, but the problem is that if you have a finite element simulation, you cannot apply a direct 3x4 filter.
No, I understand. Thank you.
I mean, you can also try to basically, of course, interpolate everything in a structured grid. Typically, I see that many people do that actually. So they do the mesh refining where they need, and at the end, they just interpolate everything in a structured grid. But then you have the space that is very big, because typically, if you want the level of detail you are interested to, that means that you have to interpolate on a very fine reference mesh. So, and instead here, you don't need any other operation in the middle. You take just your snapshot, and you basically pass through this network. At the end, you jump off with this latent dimension, and you're done. You can exploit it exactly in the same fashion of the POD. Okay? But that's only the reason. And yeah, I have at least the comparison for all the time instants that there were in our problem. Okay, maybe just start from the plot. We can see that for the multi-phase problem, we are actually able to reach, to reduce a lot the error. I don't have any relative increment there, but yeah, is quite better, and it's quite, especially, it's much more important, it is better in all the domain, not just for the candidate solution that I'm showing you here. So for all basically the snapshot, we are able to perform quite well at the level of compression. For this part, if I remember correctly, Dario, you can correct me, we use a dimension of 30. Both for the POD and both for the continuous convolutional. So just to try to give you the important point of this filter, as Sajjad already asked, at the end is just the continuous version of the standard convolutional network. So you have to use it only if you have some unstructured in your data. But if your data are images, please don't try to go with this. It's very, very similar to the filter. And also one example that I have no time to show here is we try to do the same operation on images, so structured data with the standard filter and our continuous filter, and we reach actually the same result. So at the end is exploitable also for that part, even if it's not that efficient. So I don't suggest to use for structured data. Yeah, the kernel itself is not anymore just 2 degrees of freedom, but is a multi-layer perceptor. So it's a surface that is trained during the network in order to basically minimize their loss. And one very important point, in my opinion, is that contrary to the standard filter, you can have a lot of different possibilities regarding the stride. So in the standard filter, you can choose how many cells you have to move on one direction, on the other direction, how many jumps you have to do, and blah, blah, blah. But at the end, you are still limited to the fact that you are in a structured way. With this filter, instead, you can have like non-overlapping, of course, this you can do also on the standard one, but you can have irregular stride. So this situation, you can't basically model with a standard filter because you are always needed to move in a grid in this way. You see, you can't do in the middle of this part because, of course, everything is discrete. In our extension, instead, you can do basically whatever you want. You can have also some zoom effect. So our idea is also to try to exploit this filter to see if we are able to find structures that are redundant but a different let's say a different scale somehow. We haven't tried it yet, but it's in the plan. So coming back to the conclusion, yeah, very, very versatile for the strides where you want to move your filter. What's the problem? Of course, basically this operation that I show you is easy. It's easy for us to, when you have a few points, a few dimensional, but actually looking at the points that are inside this box, if you have billions of points, is quite expensive. In a linear search, of course, you can try to do it in a more sophisticated method, but it's not easy. So you have, this method is for sure not that efficient like the standard one, but thanks to the possibility to avoid the interpolation step and the preprocessing, blah, 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 it gives you a very great result, especially in dealing with simulation data. This is the very important news. Okay, last part. Okay, it's almost 1 hour, but it's very short. So it's work that is we submitted very, very recently, like 10 days ago, and done by Marco and Gianluigi. And in this case, yeah, as I said at the beginning, the idea is to try to post-process the result of the POD model in order to improve a bit what is the final result. So typically, in a POD model, you have basically this equation. So your high-fidelity solution is basically equal to the POD one, except for a minimal error that you are introducing due to the simplification. Of course, if this residual is quite small, you can basically neglect it, and in all the POD framework, basically you do that. But our idea is maybe just to think like we have a very few snapshots to build your POD model, and so you have, even if the problem is not that complex, you can have maybe that the accuracy is not doesn't satisfy you. So what if we try to learn that quantity that depends, of course, on the problem and implicitly also in the spatial dimension? In this case, is basically hidden because I'm using the discrete solution, but you have that the error, of course, depends also on the spatial coordinate. What about if we try to learn such a residual with a neural network? Because we already have everything. So we have the POD model and the original snapshot, because for sure you have the original snapshot to build the POD model, otherwise you don't are even at this stage. And so maybe we can try to exploit everything. And this perspective, you can see like a multi-fidelity approach, in the sense that the POD it becomes actually your low fidelity model. So you want to learn the difference between your low fidelity model and high fidelity one. What's, of course, the final goal, if you train this quantity over all the input snapshots, so the snapshot that you already had computed for building the POD, you can basically interpolate, you can infer such a model, such a residual model, even in the testing point, in order, of course, to improve the accuracy. So this is the scheme. Is basically the top line and the bottom line present you two different approaches to obtain the same result, but in one case, we have the standard POD model. So you have the parameter as input, and you want to obtain the solution corresponding to that parameter. In the bottom line, just to explain you, we have instead the gap POD model. That is very closer to the standard POD, but the difference is that as input, you don't have the parameter itself, but maybe just information in some sensor of your domain. So think about like, I don't know, environmental simulation. You typically don't have the parameter as input, but you have the sensor, for example, of the water in some specific point, because it's the only sensor that you can actually put physically to measure the real quantity. So you don't have a parameter, but you have sensor data. And you can use this method in both ways. And in this case, I'm using interpolation, but if you want to exploit with the intrinsic model, I think you can benefit as well of this structure. So the idea is we start with the high fidelity database. It's needed for sure, because otherwise you can even compute the POD. And yeah, applying POD with interpolation. Well, in this case, you don't even need the interpolation. You can just compress everything into the reduced case. You hand with this low fidelity database. So you have this for the same parameter, the high fidelity solution, the low fidelity one. So at the end, you can exploit this information, just minimizing this quantity thanks to a neural network. In this case, just to inform you, we use a DeepNet. That is a network introduced by Kanadakis that basically hands to approximate operators. In this case, we don't. I mean, you can also think this stuff like a residual operator, but I mean, the main reason to go for DeepNet is that we want to maximize the generality. So typically, multi-layer perceptron are great powering approximate every function, but I mean, they are not that good in the testing error, where DeepNet basically limits the error that you are putting on the testing point data. So at the end, just to let you see the entire pipeline, you have the parameter. Everything is already trained, so you have already all the components. You have a new parameter. You can ask for the POD solution for that. Very easy. This is the standard POD with interpolation. You can ask, of course, for the residual at that specific input, and you have just to sum these two things to have the final prediction. So it's just the sum of the POD model with a nonlinear network in the middle. So the first one is everything from here is linear, then you can have a nonlinear addition that wants to improve, of course, the final result. Just a few plots to show you that things can work. So we tried, first of all, to see the difference using the GAPI POD. So here is just we have a two-dimensional parameter here. Basically, we tried to measure the relative error in all the domain using the standard GAPI POD. So what if we don't use the residual learning addition? Basically, try to fit a DeepNet model only with the high fidelity data, and then combine the two things like in the schema I show you. And as you can see, of course, I mean, it's not really understandable from just the color, but if you try to have a look at the best performing plot, you can see that our method is able to almost to be the better one in almost all the domain. And of course, here you can also show some distribution of the error for all the snapshot. Of course, just to point here, I have some visual sketch. We have here the two things. So yeah, the red line is actually the multi-fidelity approach, so the DeepNet plus the POD. And in almost all the cases, we are able at least to improve a bit. Of course, here you can see that you have a very, very large error, but compared to just the blue line, that is what is the result of the GAPI POD, at least you can improve a bit. So better to do nothing, let's say. Here again, another example, still with the Navier-Stokes, where again, we can see that putting the two things together is definitely better than just exploit in the standalone fashion, let's say. So in this case, just to conclude something, we have a post-processing. So everything has been done after the POD is something that, of course, you can also apply if you already have a POD model that maybe, I don't know, comes from another project. So if you are not able to anymore to rebuild your POD model, this is a possible way, at least, for improve a better result. In this case, we use everything data-driven. That means that we just take the snapshot and we minimize the loss function of the DeepNet using the data. But typically, you can also put some information about the physical equation that are in your problem, because in that case, the residual learning is able to do even better, in my opinion. But of course, you need to put information about the model. Yeah, of course, if you can do as many snapshots as you want, probably this method is not very useful for you. Because if you can go with a very, very accurate POD model, as you can see from these two plots, you can see that the red line is not anymore able to improve much more. In the sense that here, POD is not that good, so we get an improvement in all the domain. For the second part, where we just add some modes more in the POD model, things, I mean, the good point is that we are not able, at least with DOT, to get worse results, but we don't actually gain nothing. So please take into mind, is very, very well suited if you have a few snapshots, but if you can do as much as snapshots as you want, probably try to find something else. So the last take-home message is, I show here 3 different examples of how machine learning and reduced order modeling can be integrated. But I mean, the very, very important message, in my opinion, is that try to not just replace what you did in your previous experience. So we are a ROM-based group, let's say. We work a lot with the POD. Basically, all the numerical group in the world have worked a lot with the POD in the last 10 years, more or less. especially because the applied level is a very nice tool to have low light simulation. But yeah, instead of replacing everything with neural networks, try to think about integrate your previous knowledge with some new exotic method. In this case, it's just a neural network, but also for others, example, I mean, you can think a lot of things that, I mean, probably gonna benefit much more if you try to mix with the consolidated method is kind of just used as a new innovative tool. Regarding the software, all the method that I presented, except for the residual learning, so for the last one, are already available in EasyRead. That is our package for non-intrusive model order reduction. Instead, the continuous convolutional filter is already on PINA. That is basically our package to try to model PDE or anyway differential equation with neural network. So this is just the references. I mentioned the three main papers for the work I presented here. So with this, I can conclude. Thank you for being here. Thank you for the attention.
Thank you for the response. Now is the question time. So who is online, you can simply unmute yourself or question on the chat.
So about the code of the ShiftNet, it is available as a Fluterion in the EasyRead, yes?
Yes, actually it's not in the default branch. It's on a separate branch that I'm working on. Okay, so you can find the code, but it's not in the master one. But
can you share it between a Slack or something like that?
Yeah, it's already public, but it's not in the master branch. Anyway, I can indicate the link. Yeah, just one suggestion, please. Try to use the code that is already available. Okay, for that part, for continuous convolution, blah, blah, blah. Because otherwise, we are basically just doing redundant work.
Great.
So if you want to touch something, yeah, you're in the perfect place, but try not with my library. I'm not telling that you have to use these two, because of course, if you have a specific need, probably there is something else. But there are a lot of libraries, so instead of just make our own code, each one is better to try to at least integrate everything into a unique framework. Okay. Yep.
So I wanted to visit your shifted POD. So what are you shifting? You're shifting the POD basis itself, right?
The POD basis.
In the shifted POD, your focus section of your shifted POD.
I'm not shifting the basis. Actually, everything, all the shift is computed before having the POD basis.
So
Okay.
the shift is completed. Okay.
I shifted the snapshot itself.
Okay.
In order to gain something. The way you are talking about, I think, is from a day. I don't know if someone in the room can confirm or not. Anyway, there are other groups that basically, they don't do, of course, the same thing, but they do very, very similar, moving, shifting the modes.
Mm-hmm.
And of course, you can see here that you get the same result, basically, for a very simple problem, because instead of moving the snapshot and taking one mode that is basically this wave, you have one mode computed only in one snapshot that you still are moving in your time-dependent problem. So actually, the two things are very, very similar, but we tried to basically shift everything at the beginning.
So the data itself is shifted.
Yeah, only shifted, not transformed. So I'm not changing the height for the value of the snapshot itself, but I'm shifting, of course, the spatial coordinates where they are defined.
Trying to understand how do you apply it for something like that. For example, let's say your first image, that's my true solution.
Yes.
And keep that image static, and let's take the velocity and it's moving in time with that velocity.
Yes.
Everything over there is this part. So So then how would I go about that? Because then you are projecting your whole data on something reference, which is your below plot. And which is not.
No, this is not a projection. Huh? It's a shifting.
Okay, you're shifting. Let's say shifting. Okay.
Okay.
Okay. So
This is the operation. You take the snapshot.
Yeah.
You add the shift.
Yeah.
And you're done. I mean, everything to be closer to your reference domain, to your reference configuration. Sorry. But I mean, the y, so the snapshot itself is the same. You're just moving the spatial coordinates somehow.
No, that I understand. I'm just trying to figure it out how to use this in a more efficient manner. Probably.
You want already to improve it?
No, not to improve it. Not to improve
I don't
it.
know.
I'm trying to understand the practical application of it. For example, if there are two points A and B, they are moving somewhere, and they maintain their distance between the two. Let's say
2 points that are moving.
two bodies.
Okay. Yeah.
Two bodies, they are moving in space and time, so you don't have a reference now because body A and body B does not meet each other in their life, they maintain their distance. Yeah, more complicated.
I put a question mark exactly because of that. So I told you that we are not really ready to go for a very complex problem, like one way that is splitting, or you have 2 ways that are intersecting the other stuff, because I know that for sure this is going to fail.
Okay.
But if you have just a transport field, so you have a CFD simulation somewhere with, of course, some transport effect, it may help you in obtaining some better POD space. Of course, it's not a guarantee, but you can try. The only thing you need is to train two networks to obtain.
But would you, okay, so complex problem, okay, so I dropped my problem, but I want to come back to that problem. Do you think that if I shifted my POD basis instead, it would be much more generalizable for solving complex problems? What do you think? Because it's already on a reduced dimension.
Yeah, actually, just shifting the modes,
Yeah.
I see the same limitation that you can have also in this
The
case.
same thing, I see.
In my opinion, yes, but I never tried. So to be honest, I don't know. But if you have 2 points, so just take the example, 2 points that are moving, I don't know, in some way, and you want, how can you, where you want to shift your modes?
Mhm.
Because it's a question that I cannot reply. I mean, both for the snapshot or for the modes. If you have a very complex problem, in my opinion, the shift part has to be improved a bit. You don't need anymore a shift, but you need a transformation.
Yeah, exactly.
So just not curiosity related to the complex problems, like all these results are just like linear advection with constant or non-constant velocity. Issues that are like considered at this point.
The problem here was quite simple. I don't honestly remember how we set the condition for this kind of problem, but I think it's not constant.
Yeah, okay, but at least it's not like a full system of equations. It's just like a solution which is transported.
This is an Navier-Stokes equation.
Okay.
No, well, not a Navier-Stokes, but we have for sure the nonlinear term.
Okay.
No, Giovanni is not here, so he cannot confirm, but anyway, I'm pretty sure about that. This is an open form simulation. Only in the example I tried, this is, of course, just an algebraic equation, but here we solve, we have for sure some transport term. I actually don't remember much more, but in the paper, you can find everything.
Mm-hmm. Yeah,
No?
I can find it, no problem.
Also, yeah, for the multi-phase anyway, we also tried this one, of course, with the shifted POD, and here I'm pretty sure is a multi-phase Navier-Stokes equation.
Okay.
So for this, we have air water with Navier-Stokes in open form. It's a 2D domain, but anyway, it's quite. I mean, with the POD, we are not able to reach that good result. I didn't show here because, of course, the one with the convolutional filter are even better. So prefer to not. They can correct me after 2 slides, but you can find also that spaces. Yeah.
In the one where you use a connector. So tell me if I understood it. You first calculate the field, and then from there you do
the field, do you mean?
Yes.
Yeah.
You first calculate that, then you do like a UPV minus that one, and you learn on this.
Yeah, I mean, you create, you have the snapshot, 10 snapshots, high fidelity. You create the 10 snapshots that are in the PUD space. So just basically projecting everything into the PUD space. And yes, at the end, you learn this quantity. So the difference between the two. Is that this?
Yes. So to the deponent, you pass the parameters with the parameter.
Yes. Actually, we pass the spatial coordinate and the parametric coordinate.
Okay.
So here, just to clarify a bit, here you are on a fixed space.
Yeah.
You collect everything into one Hilbert space, let's say your discrete space, but to basically to maximize the generalability of the deponent, and also to maintain basically the dimension of the network not that huge. Because if you think like a network that has just the parameter as input, but it provides you the residual over all your Hilbert space, if you have a very, very high dimensional space, basically you are stuck because you can't train such a model. It's a model with one input and, I don't know, 2 million of degree of freedom as output. So it's not really feasible. But if you go, I mean, if you try to make it continuous even at the spatial domain, you have actually 2 inputs for just 1 output. So very, very small network, and you can at least exploit without becoming crazy to train it. It is one of the most criticality at the moment. I still see. Is more clear? Great.
So I have a question about what you just said about the continuous convolution. I talked with Dario about this one. I didn't get an answer. I think see the expensive aspect of it, that we have to search all the points, and for all points, for example, if you have 1 million points, you have to do an if loop for other 1 million points to check if they are in the neighbor. Do you have any idea how to decrease it? Because I have this issue
with a tree. With a tree, a KD3.
You mean it is in the side library?
Yeah, SciPy is there for sure. The problem that you have to implement in Python to avoid the gradient loss, to avoid to loss of the gradient information.
Yeah, actually, there's also some library which is called Pi, so it's implemented in Meta. It's completely different Python, which we are thinking to put it in our framework already, so to speed up a bit.
But I mean, the problem of finding points in a very large data set, database, I mean, I think the best solution is always go for with a tree. Because at least you have the logarithmic division of your domain. So instead of scaling with the number of points, you scale with the number of subdivision you did. So with the logarithmic of the number of the points. It makes a lot of difference when you have 1 million points, of course.
What is it called? What is it called again?
What's the library?
The method, what is it called?
A tree. KD3 is called. So K-dimensional tree. Because of course you can have 2D3 if you are in 2D domain, 3 KD3.
Yeah, okay. And you're exploring
3 KD3, and it looks
and you're exploring dimensionality of 30 for this problem somewhere.
30 not. We use 30 for this one, I'm pretty sure. For the other
30 dimensions.
Sorry?
What are the dimensions? Dimensions 30, right?
30. Yeah. The latent dimension, the reduced dimension is 30 here.
Okay.
The snapshot is around 20,000.
Yeah, totally.
Okay, I think we are in enough time, so if you have other questions, maybe you can.
And the coffee, guys.
See you next time.